So, so my talk will be quite different, as I will be focusing on galaxies in other band. So during the past few days, most of the research are related to gamma ray galaxy observations in UV, optical, or infrared. So there are lots of beautiful images made in this band. For example, I just randomly choose 2 galaxies from the internet. So you can see these galaxies in this band usually observed. So my talk will be more related to galaxies in like gamma rays or radio or X-ray. So I'm trying to argue that the observation of galaxies in other bands may also contain important information on galaxy evolution. So let's first look at the physical processes governing galaxy evolution. So I just write down 4. These are all usually chosen in people doing semi-analytical models or galaxy simulations. People usually put in gravity, cooling, star formation, and stellar feedback. And we can compare simulation results with observations. And we can change our parameters in this subgrid physics and try to match observation. Sometimes we found problems. Sometimes we can fit very well in some respects. And the question I'm going to ask is, are we missing any other important physical process? Is there any other important physical process? And so we will try to study this problem in other band. So specifically, I will look at the Milky Way galaxy in gamma ray band. And you can see in gamma ray band, you can still see the disk dominating the gamma ray emission. And this image more precisely is the all-sky Fermi view, about 10 GeV. But in the halo, you can still see this extended diffuse emission. And it's probably better to see here. You can see there are diffuse bubbles above and below the halo. And remember, this is the image produced in the galactic coordinates observed from the solar system. So in physical coordinates, the bubbles are more extended. So this is an artist view of these bubbles. And so in the rest of the talk, I will try to discuss the possible origins of the bubbles and why this event may be important for galaxy evolution. So originally, these bubbles, like in 2004, have been seen in microwave by WMAP. So at that time, the microwave data is actually not as good as gamma ray. So they don't know there are 2 bubbles. Originally, people think just only 1 bubble, one just the microwave access towards the galactic center. So people originally thought that's sequential or dark matter annihilations. So now if you look at the gamma ray, this morphology and the sharp edges, clearly you can say probably these are not dark matter annihilation. So when we try to understand what makes the Fermi bubbles, we should look at if there are other similar bubbles in distant other galaxies. And these are the bubbles we see in gamma ray in the Milky Way. So are there any other similar events in other galaxies? So the first thought you have is probably galactic winds. We have seen lots of galactic winds from some centers of galaxies in many systems, especially in star-forming galaxies. And so people have been proposing these Fermi bubbles are actually galactic winds. So galactic winds can be produced by starburst events or aging events. So both possibilities are possible. But the problem for this scenario is usually when we observe galactic winds, we observe them from thermal emissions, from the line absorption or from some emission lines. It's usually not this non-thermal emission. So it's unclear if the high energy particles if there are so many high energy particles in galactic winds. So we haven't seen any galactic winds like in gamma ray or radio. This is the main problem. So the model we propose is these Fermi bubbles are actually produced by aging jets. The main motivation is because we have seen lots of these aging jets producing these PPC-sized bubbles in other galaxies. Most of them are observed in elliptical galaxies, but some of them are observed in disk galaxies. Okay, so here are 2 other images. You can see this is MT7. The radio jets are producing these bubbles. And this is thickness A. So there are actually many more systems when we observe these aging bubbles in radio, but we don't see them in we don't see the jet directly. It's because just the jet has been turned off, probably just like the Milky Way, the Fermi bubbles. But there are many of these systems you can see the jet directly. In here, you can see the jet. So these radio bubbles actually are synchrotron emission of high-energy relativistic cosmic electrons emitting in the magnetic field. So these high-energy electrons, they can also produce gamma rays by scattering, inverse Compton scattering with some CMB photons or stellar lights. And also, there are probably also relativistic cosmic protons inside the bubbles. And these protons can also produce gamma ray emission. So in other these systems, we don't resolve these gamma rays because the gamma ray observation has very low sensitivity and low resolution. So we don't see them clearly. It's only in our Milky Way we can see them in gamma ray. And also in the nearby Centaurus A, gamma ray observation can also resolve these bubbles. So the question so the main question we want to answer is if these Fermi bubbles can really be produced by a recent aging jet event. So to answer this question, I did some simulations. So our simulations are basically hydro simulations. We also additionally follow the evolution of cosmic rays, because these cosmic rays are producing this gamma ray emission. So here are a typical run. For more details, you can look at our paper, which will appear in APG next month. So this shows the cosmic ray distribution. As the jet is only active for a short amount of time, and the age of this bubble event is like typically 1 to 3 million years. It's actually the age is very short. Now let's compare with observations. So since such a simple jet simulation can reproduce many bubble features, like the location of these bubbles, it's just near the galactic center, and the size is KPC size. I show this dotted line is the edge of the Fermi bubble, the observed Fermi bubble. And also the edge is sharp. So the main discrepancy is actually our bubble edge is irregular. So the observed Fermi bubble have very regular, smooth edge. So these edges can probably be removed by shear viscosity. If we put in a little bit of shear viscosity in hot gas, and this viscosity can just so this instability, the Kelvin-Helmholtz instability at edge can be suppressed by shear viscosity. So the other possibility is the bubble, probably the edge is much shorter. If the bubble edge is shorter, then there's no time for this instability to develop. How do our model compare with the Fermi observation? The Fermi observation observe this morphology. They also detect the flux and the spectrum in gamma ray. So this is spectrum between 1 to 100 GeV. And so here I did two models. So the gamma ray emission can be produced by relativistic electrons or protons. So in electron scenario, we found the required cosmic electron pressure inside the bubble is much less than the simulated pressure. So, but it's very different. In the proton scenario, the required cosmic proton pressure is very high. It's probably dominating the bubble pressure. So in other words, it's much easier to produce gamma ray emission by electrons. And the both theory will be proposed to explain the gamma ray emission from the Fermi bubbles. So why are one more slide. What's the energetics and age of the bubble event? So in our model, there are lots of model degeneracies. So mainly the energetics is between 10 to 55 to 10 to 57 erg. The age is around 1 to 3 million years. And the jet duration is even shorter. And so why is this event relevant for galaxy evolution? So here, if you look at the thermal gas distribution, you can see as the bubble are produced, they produce a shock. The shock are propagating into the halo. And this will have a dramatic effect on the gas distribution in the galaxy. So has these shocks, if we have any observation evidence for these shocks. So this is the shock we see in our simulation. At the shock front, the gas density and temperature is very high. They will emit in X-ray. So this is the X-ray image from the LOSAT telescope. You can see this shell structure, the shell-like structures. Originally, there are lots of different scenarios to explain these shell X-ray structures. Like in SOFIU, they propose these shell structures are produced by like a starburst event at the galaxy center, like 10 or 20 million years ago. But in our scenario, we can explain them by just this aging jet event, the Fermi bubble event, with much higher energy and a short time scale. And if this is true, if this X-ray shells, these shells are also seen in radio, because in radio you have this cosmic energy particles are accelerated by the shock. And this shell, if this is true, this shock can just propagate out and probably lead to baryon cycles in the circumgalactic medium. And if this event happens regularly in distant galaxies, they can probably slow down the growth of galaxy. Just like Jessica just said, there are probably hot gases missing in the circumgalactic medium. They are just heated and maintained by this regular aging jet event. They just shock heated them and also sweep this hot gas up into the outside of the galaxy. And okay, I will leave this. Yeah.